Good morning, folks. How are we doing?
Good, good. How are you?
Doing fine. You survived the great pile of snow in Mankato?
Yes, it's mostly melted off the sidewalks now, but it's still sticking.
Wow.
So, I was able to get registered, by the way.
Cool. You were not the only person I gapped that on, sorry about that.
Yeah, no worries.
I have a whole workflow normally that involves you coming into my office and stuff, and of course my workflow totally went to pot here,
Yeah.
and I did not manage to keep track very well of when I'd met with people, and yeah, so I forgot to mention a couple of people, but if you're in, we're good. Oh, I don't have my video. What happened? I must have clicked something. Sorry.
Hey, Nick.
Yep.
The mathematical induction quiz is muted.
Yeah, Josh told me about that. Well, he actually told me yesterday, but I only saw it just before class. So I think it's fixed now.
Okay.
If I'm wrong, you should holler at me, but I think I unmuted it and shared the grades there.
Yeah, it's fixed.
Okay, cool. So thanks for letting me know. Yeah, that was, not great. So I appreciate the heads up. Well, let's go ahead and start. So there's a quiz due tomorrow night with a handful of questions related to proofs by induction. I'd be happy to take any questions on that today. The first chapter 12 assignment is due on Monday, and that's fairly well. It's quote unquote only 4 problems, 5 problems. Let me look. 1, 2, 3, 5 problems. So it's only 5 problems, but they're all induction problems, which means that they've got at least a base case and an induction step. So there's at least 2 pieces. So it's actually, they're longer write-ups than most of the things we've been doing so far. So, give yourself a little time to get started on those, just because if nothing else, the write-up is slower and it's got more stuff in it. So that's due Monday. So you definitely got time on that. Happy to take questions on any of that today or Friday. Otherwise, the first goal today is to go back to the proof that we did Monday and connect it to the way induction is written up in the book. So there are 3 induction theorems or axioms in the book, and none of them really look like the proof that we did on Monday. And the proof we did on Monday is in some ways more what I would expect you to do for induction proofs. So we really need to justify why it is that approach is reasonable, given that it doesn't really look like what's in the book. And what's in the book is confusing, right? I mean, there's big sort of nested quantifiers, and it's like, how does that relate to the thing that we did? How do I read that? So I want to spend a significant part, maybe even all of today, trying to go through the stuff that's in the book and connect that to the example that we did. Then as time allows, we will do additional examples. And we would probably do examples in whatever's left of today and pretty much all of Friday in whatever time isn't spent doing questions and things like that. So are there any questions about stuff before we excuse me, begin to talk about how our proof connected to the stuff in the book? Questions about the quiz, about the homework, about registering for the fall, about why it snows in Minnesota in April? I don't have answers to that one, by the way.
I have a question.
Yeah.
So, like, on 12.4D,
Yep.
it's so you can't use split off term quite right, and you said like we have to be careful about how we read that. So it's like 0 is less than equal to I is less than N. And I was just wondering how I could like use split off term with that. Like I know you said on Monday that we have to be careful with how we use it, and there are different situations regarding split
Right.
off.
So you're talking about 12.4D?
Yeah.
Because that, I think, is pretty straightforward, isn't it? Just a sec. Let me make sure I'm not missing something here. Yeah, so let me pull up whiteboard. So in exercise 12.4D, you're proving the sum over I, 0 at most I, less than N, um, 3I, 3 to the I power, equals, oh, and another thing that happens on some of these exercises is there is an assumption on the part of the book, and then therefore sort of on my part as well, that you actually remember your exponent rules from whatever part of high school or pre-calc or whatever you learned about exponents. So if like exponents aren't your thing, you might want to look up basic exponent rules or definitely ask questions about basic exponent rules. So if this is P of N, then when we do the P of N implies P of N plus 1 part, so we'll assume P of N, which is just that thing up there, and prove P of N plus 1. Now here, the split off term in this case is actually pretty well behaved because we have sum of I, 0 at most, I less than N plus 1, 3I equals 3N plus 1 minus 1 over 2. And this matches 8.23 exactly. So in some of them it doesn't, and you have to do a little manipulating. But here, this is just a straight up sum over I, 0 most I less than n plus 1. Oops, less than n. My bad. You know, less than n, 3i plus, and this goes up to n and does not include n plus 1. So we're going to have 3 to the n here. This is the last term, is the nth term. And that matches 8.23 exactly. And then 3n plus 1 minus 1 over 2. And then you go from there. But this split off term is pretty much straight out of the book.
Yeah, that's my bad. I was trying to use split off term for the base case for some reason.
No.
Which is
You
why I was
almost
confused.
always
Yeah.
you almost always use empty range rule for the base case and split off term for the induction step.
Yeah, I did that for 12.4a, but I don't know what I was doing on 12.4d.
It happens. You know, these days most of us hardly know what we're doing most of the time. So, you know, we're up and we're in a class together. We're going to call that a win. So does that make sense? That answers your question, Josh?
Yeah, it does.
Anybody else have any questions about that or other parts of the homework or the quiz? Okay. Okay.
I guess I have one more question,
Yeah,
if
yeah,
that's
totally.
okay. So like on 12.8,
Yep.
I guess I'm a little confused as to how you prove like n plus 1 with the less than symbol without using like pulling in a numerical example. I don't know if you
Right.
have to do it.
And the less than problems are often ones that people find the most frustrating, because in part we tend to have very poor rules or even intuition about how to work with inequalities. We've got pretty good intuition about what rules or what kinds of steps are legal with equals, but we're not very good typically. And you know, I've been doing this a long time, and I definitely am not nearly as good with inequalities as I am with equals. So I think that's a common concern. I think that I would like to hold off on that and try to come back to that maybe on Friday, if that's okay. If you have a more specific version of that question that you want to send me on Slack or on email so that you can sort of be moving forward, like I got to here and then I didn't know what to do, I could certainly, you know, give you some feedback on that. But I think in general, the best thing for me to do on that would be just to do a whole example. And I've got some other things I want to do before I get to that. Is that cool?
Yeah, that's cool.
Okay. Other questions?
Yeah, I'm actually wondering about question 4 on the mathematical induction quiz, the one if asking about x greater than y. I'm just kind of confused about what I'm missing on the answer.
Okay, let's see. Gotta go find quiz because I don't honestly remember what the question was. Preview. Okay. So, and maybe this is related actually to Josh's question. I don't know if this will help Josh or not, but here let's look at question 4 on the quiz. Quiz question 4 says, assume x is greater than y then which of these is true? Using basic, stuff that we kind of know. So I'm going to go ahead and give them letters here. So 2x is greater than 2y. Negative 2x is greater than negative 2y. X plus 7 is greater than y plus 7. X minus 3 is less than y minus 3. 2x minus 5 is less than 2y minus 5. And negative 2x less than negative 2y. Okay, so there's a set of options. And the goal is which, and there could be multiple ones, which of these is going to be true given the assumption that x is greater than y here. Okay.
On mine, C, the inequality is flipped the other way. So
Oh,
X
you're
plus
completely
7.
right. Good catch. Thank you. That would make a big difference. I just obviously got excited about writing greater thans. So yes, that would be 100% true. Thank you. Which of these would be true, and which of these would be false, and why? I mean, the quiz doesn't ask why, but and okay, so actually, let me give you a heads up. Looking at my answers, I've got some incorrect answers in the quiz that I need to fix.
That might be why I'm confused.
That could totally be why you're confused, because I obviously got some of my less thans and greater thans swapped around somewhere along the way and just biffed some things.
I had A and F as true, and
Okay.
I got less than half credit.
So A is true. Why is A true?
Because if X is already bigger than Y, making both of them bigger by the same size, it will still be true.
Yeah, if we double them, the proportional relationship is still going to be true. Now, notice that B is false, because if we multiply by a negative value, then that's going to reverse the order, right? If X is 5 and Y is 3, if we multiply by -2, we're going to get -10 and -6, and it moves us to the opposite side of the number line and swaps the order. So B is definitely false, but that means F is true. Multiplying by negative values reverses the order of the comparison. So if X was greater than Y and we multiply by a negative value, then we flip the greater than, in this case, to a less than. If this had been a less than, we would flip to a greater than. So F is definitely okie dokie. Now, one that I just have the answer incorrect in the quiz, I'm glad you asked about this, because this is going to confuse the heck out of everybody until I fix it. This one should be correct. No, this one should not be correct. I think, but it's marked as correct in the quiz because I think in my head, I had this as a greater than. So if X is greater than Y, adding 7 keeps it greater than Y. Like if you add the same to both of them, the bigger one is still bigger. They're just shifted ahead. So you would not flip the order here. And ditto for D. that should be incorrect, because if we subtract the same from both of them, that shifts them down but doesn't change the order at all. Yeah. And then here we have a combination of these things. If we multiply by a positive value, that keeps the order. And keeps the order, sort of like moves them both, but one farther. And then if we shift by the same amount, that maintains the order. So this should have kept, if they were greater than to begin with, it should have still been greater than. And so that would also be wrong. And I have that incorrect on the quiz. So I will fix the quiz immediately after class. When I change the answers for the quiz, it gives me the option to regrade people that have already turned in the quiz automatically. And so if you got these right, and the mistake was my part, which is apparently entirely possible, it should fix that, and you shouldn't have to retake the quiz. And I'll have a look. There aren't that many people that have turned in the quiz, so I can look at everybody that has and fix people's scores on this problem if the system doesn't automatically do it for me. So excellent question, Cassie. Thank you about that. My apologies to the world for having screwed that up. So questions about that? Does that make sense? Even if the quiz is broken?
Yeah, that clears everything up on my end, at least.
Okay. Kyle, do you have a question?
I wanted to point out that for questions 5 and 6, that they're blank answers.
There are? Oh, there are. Oh, good grief. Okay, that I can fix. Actually, I'm going to fix that right now, because that is easier for me to do than it is for me to think about. I'm not sure how, well, I think I might know how that happened, and you don't care. Me and the vagaries of Canvas are not what you're paying money for. So my bad. That has now been fixed. And in fact, let me go ahead and fix those correct answers on the ones that, on the inequality one. Okay. Yeah. Okay. So I have updated all of those. Fingers crossed it will do the regrading and life will be good. So thank you, Kyle, for pointing out that those blanks got in there. Thank you for that. Sigh. Other questions? Okay, not hearing any. Let us press on. So let's go back to Monday's example. So Monday's example. And we're going to try to see how this connects to the setup in the book, which is different than what we did. So on Monday, we proved that the sum over I, 0 at most I at most n, 2 times I minus 1 equals n squared. And we did two things. So our proof had two parts. First, we showed the base case. Which was, we showed that P of 0 is true. Oh, and I guess I should say all of this was P of n. And then the induction step, was P of n implies P of n plus 1. So we did that part by, we assumed, hello, there we go. My tablet had a hiccup. We assumed P of n, and then proved P of n plus 1. So we used that technique from chapter 4, where you could prove an implication by assuming the left-hand side and then showing that the right-hand side was true. Okay, so that's the basic structure from Monday. Are there questions about that before we start looking at how that connects to what's in the book? Okay, so we proved P of 0, and we proved this implication, P of n implies P of n plus 1, by assuming P of n and proving P of n plus 1. Now, how does this relate to axiom 12.3 in the book? So axiom 12.3, which is mathematical induction over the natural numbers, is this long, unwieldy beast, which says for all n in the natural numbers, if for all n in the natural numbers, it's true that for all I, 0 at most I less than n, P of I is true, implies P of n, then, and so this is one big quantification with another quantification as the left-hand side of this implication in the body. So this whole quantification implies for all, make sure I'm writing the right thing here, for all n in the natural numbers, P of n is true. So in this setup, this bit on the right is our goal. So this is our goal. Which is showing P of n is true for all n. In the natural numbers. So this is what we want to have happen. And what axiom 12.3, and I realized I can't spell axiom. There we go, that's better. What axiom 12.3 says is that our goal follows from the left-hand side. So if we can prove this, we'll have our goal. By this axiom. So this axiom basically gives us a new technique to work with, which says if we want to prove something like this right-hand side, it is sufficient to prove this left-hand side. Okay? Now this left-hand side does not look like an improvement. Like if I want to prove this, this looks like, oh my God, like a much more complicated and weird thing. And it's not at all obvious how this is going to help us. And that's really what the rest of today's, well, much of the rest, if not all of the rest of today's lecture, actually probably all of today's lecture, given the time, is going to be about. It's like, well, how is this useful, right? If I want to prove this, how is it helpful to say, oh, you can do this, what looks to be far more complicated thing? What does that do for us, okay? But do we get the sort of, this is our goal and it follows from this thing? Does that part of the axiom make sense before we start to take this piece apart on the left-hand side? We good? Got a thumbs up? Okay. Oh, and a thumbs up and an applause. We're totally rocking here. I'm gonna then take that as a positive thing and move on. So I'm gonna make a new screen here and we're gonna just pick up this piece and try to take it apart a little bit, okay? Now, so we had, so the left-hand side, oops, I really wanted that to be black. The left-hand side again is for all n in the natural numbers, for all I, 0 at most I less than n, p of I implies p of n. Okay, so I'm just going to focus on this left-hand side now. Now, by meta theorem 9.16, and I warned you that we would come back to this meta theorem. Meta theorem 9.16 says that a for all with not an empty range, but a default range of true, a for all, we can prove the for all by just proving the body for some arbitrary value of the quantified variable. So this is true, and by this I mean this whole thing is true if and only if the body is true, which is for all I, 0 at most I less than n, p of I implies p of n. If that's true for arbitrary and at least 0. And I get the at least 0 because of the natural numbers thing here. So if we didn't have the natural numbers, we wouldn't necessarily have that. But here, because we specify that n is in the natural numbers here, that gives us that little piece there. Okay. So this tells us, so if we, let me back up one. To prove our goal, we need to prove this thing. Meta theorem says to prove this thing, it is sufficient to prove this. So we're trying to simplify what we have to prove. So to prove our goal, we need to prove all of this. But to prove all of this, by the meta theorem, it is enough to prove this. Okay? Are we with me so far? This is the fairly deep and weedy stuff. So feel free to like express. They don't have a despair emoji in Zoom. They ought to, but you know, you could do thumbs down or repeat or something if you get questions. Good? Okay. So now, great. We got to prove this. Now, if we think about this for a second, this has got to be true for arbitrary n, at least 0. But it's going to behave really differently for n equals 0 and n bigger than 0. Because for n equals 0, because one of the things that's weird here is we've got this quantification on the left-hand side. But this quantification will collapse if n is 0 because we'll get an empty range. So I'm actually going to split this n at least 0 into two cases. So I'm going to split, let's see, because, oh, I'm in blue still, bad. Black, better. Because the quantification on the left-hand side collapses when n is equal to 0. I'm going to split n greater than or equal to 0 into two cases. Using the fact that n at least 0 equivals n equals 0 or n greater than 0. And notice that, I mean, this in some sense, this is just the translation of the English version where we say n is greater than or equal to 0. N is greater than 0 or n is equal to 0, right? I'm not doing anything very magical here. This is just literally what we say this means. So I'm going to look at what does this mean in these two cases, because I need to prove this for all n greater than or equal to 0. So I can think about what does it mean to prove this when n is equal to 0, and what does it mean to prove this when n is greater than 0. So let's start with the first case. When n is 0, this becomes for all I, 0 at most I less than 0, pi greater than p0. Right, so I've put in 0 for all the n's. Now, this part here, this is false. So we can just say by arithmetic, that's false. Right, there's no I that's less than 0 and greater than or equal to 0. And now this is empty range rule. So 8.13. And so this reduces to the identity of and the identity of and is true. And this is just P0 by 3.73. And that's our base case in the version of the proof that I did. Okay? So this says that we're going to have to prove this thing for n at least 0, and I can split n at least 0 up into two pieces, and it turns out that to prove this for the first piece through just some basic stuff that we've done and a little arithmetic, proving this in the case that n equals 0 is the same as proving p0. So when I say in the base case, we'll just prove p of 0, really what I'm doing is saying we'll prove this, which is the n equals 0 case of this thing here. But who wants to think about this ugly thing? It's a lot easier to be like, I'm going to prove p of 0. And then I don't have to think about all this other waffly stuff that was going on. But this justifies why it's okay to just prove P of 0 for the base case, because we have proved here that P of 0 is equivalent to this case, the thing we're trying to prove, when n is equal to 0. Okay? So what I'm doing here is I'm showing why it's okay to just do this when what we really need is maybe this complicated thing. But this is equivalent by this little proof to just P of 0. So it's enough to just prove P of 0. Questions about the n equals 0 case before we go on to the n greater than 0 case?
I guess I'm kind of confused by what you mean by the collapse.
Oh, I just mean that the quantifier goes away through empty range rule.
Oh, okay.
That's all I mean by collapse. Like we can get rid of the quantification in that case.
Gotcha.
And we like doing that because we're trying to simplify things.
Okay, that makes sense.
Does that make sense?
Mm-hmm.
Cool. Other questions? Okay. Then now we got to do the n greater than 0 case. So I'm going to make a new thing. And I will, now we consider the thing that we were doing, which is for all I, 0 at most I less than 0, P less than n. P of I implies P of n. And we're going to do this for the case where n is greater than 0. Now, if n is greater than 0, then sort of by arithmetic, n equals m plus 1 for some m that's greater than or equal to 0. There is some other natural number where n is one more than that. And that'll turn out to be important in a second. But if n is greater than 0, then I know that I could replace all the n's with m plus 1 for some natural number m. Okay? And I want to do the m plus 1 thing because that's going to let me do a split off term here. Okay? So then, and I should make it clear, like, I'm not ever going to expect you to do a proof like this that justifies some complex proof rule based on some axiom. Like that, this is not here because you need to do this. This is here so you can understand what the book's saying and how it relates to the things that I'm using in my examples and that I would expect you to use in your examples. So this proof, I mean, is hopefully informative, right? And should hopefully make sense, but don't feel like you're going to need to like produce one of these because that's not true. You'll need to be able to do induction proofs, but this sort of justifying how we're doing induction proofs, not something you will need to do, okay? So if you feel like you're following what I'm doing, but that you're not sure you could create this from scratch, that's fine. You're not going to be asked to create this from scratch, if that helps a little. Okay, so then for all I, 0 at most I less than n, pi implies p of n is equivalent to, by the fact that n equals m plus 1, for all I 0 at most, I less than n, p of, oh, sorry. Let's just undo our way back to here. I forgot to actually replace n with n plus 1. P of I implies P of m plus 1. Now we can use split off term here. And this is for all I, 0 at most, I less than m. So we go from m plus 1 to m. And then we have to add the last term. Since this is a for all, the operator is and this went up to m, was the last thing here. This goes up to m minus 1, but doesn't actually get to m. So m is the term we're missing. Okay. And now, if you think about it, this is, so what does this say? This says that we could prove this by proving that and this implies the right-hand side. Well, if we're doing a proof and we're allowed to assume two things, it's okay to assume only one of them. Like if I give you a box with two tools in it and I say, build me a something, if you can do it using just one tool, that's okay, right? You don't necessarily need to use all the tools in the box. And in a formal way, this is actually what rule 3762 tells us, which is, let me put that up over here. And this is in the printed things, not in the book. So 3.76.2 says that if we know that P implies Q, then that tells us that P implies, Q implies R implies P implies R. So this says if P is stronger than Q, if P's got more stuff going on than Q does, if Q was enough to get us to R, then P will also get us to R. If we can do R with just a screwdriver, we can do R with a screwdriver and a hammer, because screwdriver and hammer implies screwdriver. So in this case, we know that this conjunction implies either of the pieces. So a version of this would be that P and Q implies P tells us that P implies R implies P and Q implies R. So I'm just putting P and Q in for P everywhere in 3762. And we know this is true, right? This is just 376b. So we know that this bottom part is true. That if we have P and something implies R, that follows from either one of the pieces. And that's useful here because then that gets us, that says this follows from just P of M implies P of M plus 1 using 3762 and 376b and basically all of this sort of note stuff over there on the side. But if we can get from if one thing gets us to the right-hand side, then two things definitely gets us to the right-hand side. So that this, if this is true, that implies that this more complicated thing is true. And that's the sort of useful trick here, is we're saying we could assume P of I is true for all of the preceding values of m minus 1 and m minus 2 and m minus 3 all the way back to 0, but we don't need to. It's enough to, if it works for us, if we can do what we need to do just assuming the immediately preceding version of P, that's okay. That if we can prove this, that proves that. And if we prove that, we get back up to here. And so this is essentially our induction step. So this is our simplified induction step. And if we go back to the stepping stone sort of thing, if we think of this as P0, and this is P1, and this is P2, and this is P m minus 2, and this is P m minus 1, and this is P m. And we're trying to prove P of m, P of m plus 1. This is the goal. We're trying to get to here. My simplified version says you can assume this. Let's do this with, throw some color in here. My simplified version says assume this and use that to get to there. So do P of m implies P of m plus 1. That's this thing here. The version in the book, the full-on version, says, hey, if you want, you don't have to just limit yourself to the immediately preceding thing. You can assume all of this stuff and use all of that to get to the goal, okay? And that's really what this is saying. That we don't have to just assume up to, or this would be more with the m's. You don't have to just assume P of m, you're allowed to assume all of the p's from 0 up to m, in case you find any of the other ones also useful. So the book's version looks more powerful because it's like, here's a whole pile of stuff, use it. But it turns out you very rarely need the whole pile of stuff. Usually all you need is the immediately preceding one. And so it's easier to think about, in my experience, to start off at least by just worrying about the one right before, and not trying to do like 18 million things. And so that's why I tend to do this simplified version where we just assume the previous and use that to imply the next, because that's usually sufficient. There will be examples where we need more than just the previous one. So we will sometimes need the book's version, but usually it's sufficient just to have this simpler version. And the book's version is sometimes referred to as strong induction because you get to assume a stronger thing, more stuff. And the version that I'm using is, not surprisingly, sometimes referred to then as weak induction. Okay. And so all of this waffling around, the point of all this was just to show you that weak induction is enough. That weak induction gives us what we need to, do what it says in axiom 12.3. And again, you would never have to prove all this stuff that I just proved, but I wanted to justify, since I'm, the book's like, do this. And I'm like, yeah, I don't want you, you don't need to do that. You can, but you don't need to do all that because all of that's kind of complicated. Here's a simpler version. I felt like, I need to justify why the simpler version is okay. And this is the justification for why the simpler version is okay. Okay? Questions about all that? That was a lot. We would go on to an example of induction, another example from the book next, when we're done with this. So questions about this? Going, gone. Okay, so let's do another example. So I'm going to start with another simplish example, and that'll probably get us through the rest of today's class. And then on Friday, we can do some examples that involve less than and some of the other things that are on the assignment that would be useful. So I'm going to do exercise. Oops, I want to be back to black ink. Exercise, I'm going to do 12.4C. Which says, prove that for n at least 0, the sum over I, 0 at most I less than n, two to the I equals 2 to the n minus 1. Okay. So this is essentially saying that 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the n minus 1 is 2 to the n minus 1, which is sort of interesting. If you add up all the powers of 2 up to n minus 1, the answer is almost the next power of 2. It's one short of the next power of 2. So adding up a sequence of powers of 2 almost gets you to the next power of 2, which actually turns out to be useful and interesting in a variety of ways. So we will prove this by induction. And this is more, this is exactly the kind of thing that you would do in doing the proofs for the homework. All that previous stuff was for your grand edification, whereas this is sort of practical examples to help you do the homework. So base case, we're doing this for n greater than or equal to 0. So the smallest value of n that we need to worry about is n equals 0. So we'll need to prove that. So we need to show that the sum over I, 0 at most, I less than 0, 2 to the I equals 2 to the 0 minus 1. And so I'm going to actually just take the whole expression and show that it simplifies to something that's true. So I'm going to say sum over I, 0 at most, I less than 0, 2 to the I equals 2 to the 0 minus 1 equals. Now, as I said, base cases are frequently about empty range rules. Not always, but very commonly. And that happens to be the case here. There is no I that is less than 0 and greater than or equal to 0. So by arithmetic, we have the sum over I false 2i equals, oh, and I guess I could also, by arithmetic or exponents, however you want to do it, I can rewrite that to be 1. So n to the 0 is always, well, if n is not equal to 0, n to the 0 is 1. So we rewrote this to this, and we rewrote this to that. Are you with me? Questions? Okay. Then empty range rule says that we want the identity of this operator. This operator is plus. The identity of plus is 0. And then 1 plus 1, or 1 minus 1 is also 0. And we're done with the base case. Done with the base case. Questions about that? And the base cases are often quite simple like this. It's very frequently, not always, but very frequently the case that you're just plugging in 0 for n, and then the quantification collapses, to use the same, confusing word I used earlier. The quantification collapses through the empty range rule. So the range ends up being empty. We use the empty range rule. The quantification disappears and is replaced by a constant, the identity of the operator. And then hopefully a little math cleans up the rest. Occasionally, instead of the empty range, you'll have a range with a single value in it, and then the 1-point rule from chapter 8 would be the thing to use. But it's more common that you actually end up with just an empty range here. Okay. Questions about that? Then let's do the induction step. So for the induction step, we need to show that P of n implies P of n plus 1 for n at least 0. So we'll assume n at least 0 and P of n, which is just the thing that we had, which was the sum over I, 0 at most I, less than n, 2i equals 2n minus 1. So we're going to assume that and then prove P of n plus 1, which is for all I, so the same thing, but with n plus 1 where all the n's were. Okay. So we're going to assume this, and we want to prove this. Are we good with that? So I'm going to take the whole thing. So what I'm going to do? Next, I'm going to just take the left-hand side. So I'm going to start with the left-hand side. For all I, 0 at most I, less than n plus 1, 2i, 2 to the I. And then we're going to do split off term, because that's what we usually do. Oh, hang on. I started writing for alls here, and that needs to be a sum. And I did it here too. My bad. Thank you. So this is the sum of I. And this is the sum of, oh, wow, man, of I. Okay, whew. Sorry about that. We use split off term and we get the sum of I, 0 at most, I less than n, 2 to the I. And this is plus, summation is plus, so we have plus here. And then we come up to n. Here is the last term, so this is going to be 2 to the n equal, oh, yeah, we weren't doing the right-hand side, so we're just doing the left-hand side. Okay. Now, so that's pretty common that we do the first thing we do is a split off term. That's pretty standard. And now we need to figure out what to do next. And what we do next is usually use the induction step. So it's pretty common after we do split off term that what we have, step, that this matches our assumption, okay, which is true here. This is exactly that, which means we can replace this with the right-hand side. So we get 2 to the n minus 1 plus 2 to the n. So this part is from here, and this part is from there, okay? And then now it's just, if we look ahead a little bit, we've just got these 2 to the n's. So that's 2 times 2 to the n minus 1. And so that was just a little algebra. And then by a little more algebra about exponents, this is 2 to the n plus 1 minus 1. And we're done with the induction step. Which completes the proof. QED. Boom. So that's what your proofs will look more like. Okay, they won't look like that big complicated thing that we started with. You'll do a base case like this, plug in 0, and hopefully everything will just go and fall in on itself into something that's sort of obviously true. And then you'll do the induction step where you assume it's true for n, and then you show it's true for n plus 1. And that's usually a split off term followed by an application of the induction step, followed by maybe a little cleanup math. So, questions in the 0 minutes that remain? Friday we'll take questions and we'll do more examples, including we'll make sure we get to an example of a less than problem because those are a little weird, and we'll make sure we do that. Okay, it's been a pleasure. Hang in there. I will see everybody on Friday. Bye.
I had a question quick, if you have time.
Yeah, sure.
I was wondering if you could explain your last algebra step.
Sure. Let me get back to the whiteboard. So this step right here down at the bottom?
Mm-hmm.
Yeah, so in general, there's an algebra rule that says that x to the a times x to the b is x to the a plus b. Okay. And here we have 2 to the 1
right.
times 2 to the n. So then we have 2 to the n plus 1.
Gotcha. All right.
Does that make sense?
Yep.
Cool. Anything else, or are we good?
I'm good.
Awesome. Everybody else happy? Okay. I will see everybody later. Ciao.